Introduction to rational numbers. All right, we're in section 1.3 now. We're dealing with fractions, everyone's favorite topic.
Yeah, I love
Fractions
fractions.
are actually great. People tend to like decimals better, but I don't know why that is. Maybe after this, people will like fractions more. Okay, so let's start off with simplifying something like 6/8. Okay, usually what we think about is, well, all right, this is the usual process. 6 is divisible by 2, and 8 is divisible by 2. So if I divide them both, that'll give me 3/4, which there's nothing wrong with that. I do want to present an alternative way to look at it. We could say, all right, well, 6 is 2 times 3. All right, let's look at their prime factorizations.
Prime factorization.
And 8 is 2 times 4, and 4 is 2 times 2. So we can look at 6/8 as 2 times 3 over 2 times 2 times 2. And remember what happens if you divide something by itself, you get 1, right? So that's really just 1 times 3 over 1 times 2 times 2. And if I multiply that together, I get 3
over 4.
over 4. Same thing, right? Same thing. Notice when we did this right here, that's the same process here. We're dividing out that 2. That's the common 2 that we're dividing out. Okay. Um, let's look at buckets of water here. Okay, call it buckets. Look at boxes, whatever you want to call it. Notice this one right here. There's 1, 2, 3, 4, 5, 6 out of 8 boxes shaded in, right? So this is 6/8. You'll notice that there is the exact same amount of shaded area in this box over here, even though there's only 1, 2, 3 out of 4 shaded in, right? Well, it turns out they're equivalent, right? All that we did was just remove this middle line right here, and we were able to get the other
Oh,
box. Okay, same thing though, right? Let's do another one. Okay, so 6/9. 6/9. I want to simplify that. So 6 is 2 times 3. We already know that. We just did that. And 9 is 3 times 3. And so what do they have in common? Right? 2 times 1 and 3 times 1. 2 times 1 and 3 times 1. 2/3. Okay, 2/3. That one was boring. Okay, whatever. Let's look at the buckets again, right? The buckets of water, the boxes, whatever you want to call it. The first one here demonstrates there's 9 total equal sized pieces, right? 9 total blocks. 6 of them are filled in, so that's 6/9. Over here, we have 2 out of 3. Okay, what happened? It's the same amount, right? The same amount of shaded region, or the buckets are filled to the same level. We just took out
the dividers.
those right there, right? So 2/3. We're simplifying without even doing any arithmetic there. Okay, let's talk about comparing 3/5 and 2/3. Let's see if we can compare their sizes and decide which one's bigger and which one's smaller. So there's different approaches to this. What we could do is, I think the usual way people first learn how to do this is just to divide it out and get a decimal approximation for the values. So if I wanted to convert 3/5, I have to remember that that means 3 divided by 5. And, well, that means 5 goes into 3.
How many times?
Oh, but it doesn't go into 3, so we break out the points,
Decimals.
right? So
Yep.
point, put a 0 on the end. How many times does 5 go into 30?
6.
6 times, right?
Yay.
So that's 30, subtract, remainder of 0.6. Okay, so we could say that this is the same thing as 0.6. Okay, 2/3. Again, that just means 2 divided by 3. Okay, so 3 goes into 2. Again, 0 times. So that's when we break out the decimals. 3 goes into 20
6 times.
6 times. Okay, so that's 18. We have a problem here. 3 doesn't go into 2, but if you add another 0, it's 6 again.
Yeah. 18.
And it's going to keep going, right? So what we would do is say this is ... right? It goes on forever and ever and ever. Sometimes they write it like 0.6 with a little line on the top. Okay, that's acceptable. 0.66 with a bunch of dots after it also means the same thing. Okay, 0.6, 0.66. We can plot that on a graph, but I think we know which one's bigger. All right, so 0.6 would be here. There's our 3/5. 0.66, oops, pushing buttons that I shouldn't be pushing.
Don't do that.
0.66 is going to be about right there.
Yeah.
That's going to be our
2/3.
2/3. So you can see 3/5 is a little bit to the left of 2/3. So we can finally make a claim as to which one's larger. We would say that 3/5 is less than 2/3. Or you could also say
length greater than 2/3 greater than 3/5.
yeah. Right, so both are fine. Okay. Okay, so that's one way to do it. There are other ways. So this is probably a better way to look at it. And we're going to break out our buckets of water again. So 3/5, notice that that is a box or a bucket that's filled 3/5 of the way. And we have this other one here that's 2/3 that is also filled 2/3 of the way. You might be able to see that one's a little bit bigger than the other, but they're really close. What we could do is compare, if we could break them up into equal size units, we could then compare them, right? So I'm going to say, all right, this is 3/5. I'm going to break this up into thirds. Okay, so still the same amount. I didn't change the amount of water there, right? Still the same amount of shaded region. I'm going to break this one up into fifths. Okay. So now, again, I did not change the amount of shaded region in either square, but I did change the way we're going to talk about it, right? So instead of saying that this one had 1, 2, 3 out of 5 squares, we can say that we have 1, 2, 3, 4, 5, 6, 7, 8, 9 out of 10, 11, 12, 13, 14, 15. Okay, 9 out of 15. Boom, 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 boom. Over here, I could say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? So we're actually dealing with the same size pieces here. Dealing with the same size pieces. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 out of 15. So now it's a little bit easier to decide which one's bigger. 9/15 or 10/15. Well, the 10/15, of course, is going to be bigger. So 2/3 is bigger. Notice what we did. All right, everybody knows that phrase. What did we do? We found a common denominator, right? I guess I should write out the actual answer. I was writing it out in the bigger numbers, right? Okay, so there we go. So 3/5 is less than 2/3, or we could say that 2/3 is greater than 3/5. Okay, we found the common denominator. All right, this is just the same picture. My drawing came out perfectly fine earlier, so I didn't feel like I needed to pull this one up, but that was there just in case. Okay, so let's go back a little bit. How do you find a common denominator? Well, if you don't feel like drawing boxes, which I don't blame you if you do, or don't, then I would look at 5 and 3, the two denominators, and then decide what number do they both go into, or what is a common multiple of those. And there's a lot of answers, but you want to go with the smallest one if you can. There's an infinite number of answers. So, yeah, they both go into 15. They both go into 30. They both go into 45.
60.
We can keep going.
90.
I'm just going to go with the smallest one and say 15, right? 15. So that, I multiply the top and the bottom by 3 because that would force the bottom to be 15, and 3 times 3 on top is 9. Here, I need to multiply this denominator by 5. So I'll multiply the top by 5 as well to make it legal. And by that, I mean all I'm doing is multiplying by 1, right? And if you multiply by 1, you're not changing the amount. You're just changing the way it looks. The same way that we took 3/5 and we changed it to 9/15 by just drawing some lines, right? Same exact idea. So 2 and 5 is 10, 3 and 5, 15, and there we are again, right? So I expect most people are going to do this, but this is why it works, right? That's why it works. Okay. Now that we're having a blast, let's go on to adding some stuff together. So 3/4 plus 2/3, we're going to need to find the famous common denominator because we're not comparing the same size pieces, right? So ordinarily what we would do is say, okay, 4 and 3 both go into 12. So what I'm going to do is multiply the top and the bottom of this one by 3 to get it to force it to be 12. That'll give me 9 over 12. And we'll multiply this and this by 4 because that'll give me 8 over 12. So now I have 9 over 12 plus 8 over 12.
17 twelfths.
17 twelfths.
I like to think whenever we go to common denominators, it's like the superhero form of the number, right? They change their clothes, but they're still the same thing.
And people freak out and they don't recognize it even though it's exactly the same thing. It's like putting the sunglasses on and no one notices.
Clark Kent, man.
Clark Kent. Right, that's his name. So here we go. This right here, same example, same exact example. Okay, we have 3/4. We have 2/3. Okay, if I wanted to put those together, they're not the same size pieces, so it's harder to figure out, what I'm talking about. So what I'm going to do is say, all right, well, I'm going to break this 3/4 up into thirds, and I'm going to break this 2/3 up into fourths. Now I'm dealing with the same size pieces, right? They're both 12, right? These are all twelfths. All of these represent 12 of a whole. Okay, so this one has, I think I had this, yeah, there we go. So this one has 9/12, and this one has 8/12. And if I counted all the gray squares, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Oh, look at that. I have 17 pieces that are of size 12th, a 12th. Okay, so just breaking it up. Always getting those equal size pieces. All right, this one's a little bit boring because we already did most of the work for it. The only thing different is the subtraction. So we already said that this is 9/12, and we already said this is 8/12. And so 9 minus 8 is 1/12. In other words, what are we talking about? Oh, look at that. There's our buckets again, right? This time, I put this one in this reddish color because I wanted it to represent
The
something.
negation?
Yeah, we're taking it away. Yeah, we're taking that away. So this is the amount we want to take out of this one here. All right, so did I draw lines? Yeah, I drew lines already. Okay, good. So here we have, again, the 9/12. And here we split up the negation part, right, into the 8/12 that we're taking away. So I can actually just go right here and say I'm taking away 1, 2, 3. I guess I should take it away from the top if it's a bucket of water, right?
Right.
1, 2,
Be hard.
3, 4, 5, 6, 7, 8. I took 8 away. Look what I'm left with. I'm left with 1/12 of the original. All right. Good stuff. Let's do some multiplication. All right, so typically when you're multiplying, you don't worry about common denominators, right? All you look at is, well, you multiply the tops and the bottoms, okay? Now, I will say that that's not the best way to approach it, so I'm going to write this a second time. 3/4. I will always advocate for doing it this way in a second. But, okay, 3 times 2 is 6, and 4 times 3 is 12. 6/12, well, 6 is half of 12, so that's 1/2. Okay. I like to do it like this, where I say, well, 3 divided by 3 is 1. That's 1 over 1. And 2 over 4 is 1 over 2. So really, this is just 1 times 1 over 2 times 1, which is 1/2, right? I like that way because it's smaller numbers. You can divide before you multiply.
Do you ever put them together?
As in
Like one big fraction?
3 times 2 over
yeah,
4 times 3. Yeah, that would work too.
And
then you could definitely split it up by prime factorization. Because 4 is 2 times 2. I like this. Now it's all on 1. So 3 and 3 would cancel. 2 and 2 would cancel. You still get the 1 times 1 over 2 times 1 times 1. It's a half again. All right, multiplying fractions is probably the easiest operation with fractions. But let's talk about some more buckets here, right? So we got this. We'll think about what 3/4 times 2/3 means, right? It means you have 3/4 of 2/3. So I drew the 2/3 bucket first, right? So that one's filled 2/3 of the way. And so here I went ahead and broke it up into common pieces, right? So 3 and 4. I know we don't find a common denominator, but it's still nice to be able to look at it with pieces that are the same size, right? So this is actually 2 squares over, or yeah, 2 squares over 1. The gradient part still represents 2/3, but this over thing, you see 1, 2, 3, 4, right there, that's my fourths. So we broke up the 2/3 into fourths, which gave us 12 little boxes. Okay, whatever. We got 12 little boxes. So now, if I wanted 3/4 of these, that would be here, there, and there. There's 3/4. Okay, so if I wanted 3/4 of 2/3, that's this piece right here. That's what this is showing right here. All right, so that darker region right there, that represents the, well, 3/4 of 2/3. So there's 6 there out of 12 total. Okay, let me raise that up a little bit. There we go. There's 6 out of 12 there, which, okay, we already know it's a half, but let's talk about why it's a half. There's 12 total here. There's 6 boxes here, and then there's 6 boxes right here, right? So it's half. There's 6 and 6, so you can split it up into 2. So this is 1 out of 2 pieces the same size. Okay, it's kind of harder to see it that way. Maybe if you decided, if you get creative, you could take these 2 blocks right here and move them up there. So now those 2 blocks are going to be gray. Maybe. So now you can actually see the clear line. Yeah, maybe. That's a little bit harder to do, but whatever. Not important. Let's do one more. Some division. I like division. All right, 3/4 divided by 2/3. So the rule, we'll do the rule first. The rule doesn't make a lot of sense on its own, but the rule first is you take the problem, you multiply by the reciprocal. You multiply by the reciprocal. You don't divide really anything. So now you're doing 3/4 times 3 over 2. 3 times 3 is 9. 4 times 2 is 8. So 9/8 would be the answer. And that's the most straightforward way to do it. Let's talk about why. Let's torture ourselves a little bit.
Right.
Okay, so here we have 3/4, and here we have 2/3. Now I'm saying this is 2/3 because we're dividing 3/4 into 2/3. In other words, let's think about buckets again, right? We have this bucket of water that's 3/4 of the way full. We have this new bucket over here that's 2/3 the size of the original. So you can see that here, right? There's 1, 2. This dashed region is just to show you that it needs that part of it to be able to be as tall as this one. Okay, so now the bucket is empty. I want to move this water from here to there. Okay, well, my problem is I need some way to compare them. So again, common size pieces, common denominators. Let's do it. So we're going to chop this one up into thirds.
Can we freeze the water?
And then we can chisel away at it.
Yeah, exactly.
I like it. Get a saw. What's an ice saw?
I guess that's
I
saw?
figured you would know.
No, I wouldn't know. Well,
maybe.
That would be something.
We could use a saw.
Saw.
So gas powered or electric.
Either way.
Either way. Okay. And so now we have equal sized pieces, but I want to pay attention to something here. These are no longer, in the new bucket, these are no longer considered twelfths, right? Because there's only 8 of them. Again, this region up here doesn't exist. So what was once a 12th over here is now considered an 1/8 over there. An 1/8 of the new bucket. Okay, so now we're going to fill in the new bucket with the old bucket's water. All right.
Old bucket's ice.
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 Well, it's still water,
Yeah.
just really
Frozen.
cold.
The
frozen water. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 pieces. Okay, so let's go ahead and start transferring that over. So we got 1, 2, 3, 4, 5, 6, 7, 8. This bucket's full. Let's go to the next bucket. 9. We have now 9 pieces. And how big are those pieces?
They're eighths.
They're eighths. So we have 9/8. So that 3/4.
Oh, scroll up.
Oh, can't see it. Let's do it like this. There we go. That 3/4 is now 9/8 in the new buckets. Okay, and I think that's that.
Done.
Boom.
Yay, numbers.